So my name is David Hicks, and today I'm going to be talking about structural analysis tools and methods of generation, crystal structure generation in AFLOW. So originally we've been talking about more of the database aspect of AFLOW, and now I'm going to touch on just a very brief segment of the software tools that we've implemented. And so in particular, I'm going to be focusing on structural tools. So there's going to be three that I'm going to highlight kind of quickly, but just to give you a brief overview. So we'll start with AFLOW-SYM, so our Symmetry package that we've developed. And then next I'll be talking about the prototypes that Cormac and Marco have already alluded to. And then finally, I'll talk about this new tool we've developed, XtalFinder, which helps us to reduce duplicates in our data sets. So it helps us to identify unique structural prototypes, remove duplicate compounds, and also to classify structures. Okay, so first, as I said, we're going to start with AFLOW-SYM. So this is our Symmetry package that we've developed, and this module tests the invariance of a crystal under transformation. So typically we're given atom positions and lattice vectors, and we want to know the symmetry of these objects. So we want to find, for instance, the mirror planes of the crystal, the rotation axes, screw axes, or glide planes. And with these collected, we can determine certain symmetry attributes, such as the space group, Bravais lattice, and Wyckoff positions. And so this is a nice tool because if you could actually use these symmetry descriptors potentially as features, since we've been talking about machine learning all week, you could potentially use these as descriptors or features in your model. So I'll briefly highlight how we actually calculate this, because it's not as straightforward as you might think. So for example, if we have an arrangement of atoms, so we have this diamond arrangement, and we want to know whether or not this exhibits fourfold symmetry. So to do this computationally, we actually have to take the atom positions and rotate them by 90 degrees. And we want to see whether the original atom positions or the transformed atom positions map back onto the original atom positions. And so there's three scenarios here. So we can see that if we perform the transformation, there's essentially three possible outcomes. One is that when you perform the transformation, the original and transformed atom positions line up essentially exactly. And so if you do this, then this would be considered an isometry of the crystal. So this particular symmetry operator maps to our crystal. Alternatively, on the other end of the spectrum, you may have this scenario. When you perform the transformation, you actually don't map back onto the atom positions. So in this case, at the bottom here, we have twofold symmetry, not fourfold symmetry. But actually a more realistic case is this middle scenario here, where, I'm getting ahead of myself. We have this middle scenario here, where when we transform the atom positions, they don't exactly line up with the original coordinates. And so the question is, should this be considered a mapping of the crystal? And so this is really a tolerance issue. And so since we're working with real coordinates, real numbers, we need to have a threshold for when we can say atoms map back onto one another. And so this is the general criteria that we need to check. If the original atom positions can be mapped onto the transformed atom positions and they're within some tolerance threshold. And we need to do this for all of the objects, or atoms in this case, in our system. And so for molecules, this can be straightforward because we don't have periodic boundary conditions. But again, we've been talking about inorganic crystal structures. And so really we have to be careful when we do mappings because we have to consider periodic boundary conditions, so the method of images. And then also a lot of times when we're doing this computationally, we flip metric spaces. And so we can actually get non-uniform metric tensors, which can mess up the mappings. And so these are just three different aspects that I've highlighted that in our code that we're careful to consider. And so this is kind of goes above and beyond some of the current packages that are available. So for example, as I mentioned, we have a robust mapping procedure that's accurate in both direct and reciprocal spaces. And so we have these consistency checks. So if we're determining the dual, the symmetry in dual space, it's consistent with real space. And so, for example, in this case, another thing we consider is if we have a system in Cartesian coordinates, a lot of times we transform into fractional coordinates or the lattice basis. And so depending on what our starting lattice is, the metric can change, the metric tensor. And so if we have a triclinic lattice here, when we actually transform to fractional space, which converts everything to a unit box, we get this shearing of space. And so you need to be careful when you're performing mappings depending on what representation you're using. And so a lot of these packages may not take this into account. And so this is something that we're careful to consider. Additionally, we have this adaptive tolerance scheme. So for example, as I mentioned, tolerance plays an important role in determining the symmetry. So somebody asked if I can elaborate on the fractional space. Sure. So typically when we're modeling a crystal, we'll see a little bit later that we use a geometry file, and you can specify the coordinates with respect to Cartesian coordinates or what are called fractional coordinates or direct coordinates. And so basically they're fractions of the lattice vector lengths. So maybe instead of, it might be half, half, half to represent something at the center of the unit cell. So this is fractional. Yep. And so, but yes, the thing to keep in mind is that if you do this, when you convert to this lattice basis, you might actually be warping space. So that's the idea here. So for the adaptive tolerance scheme, as I mentioned, tolerance plays an important factor. So for example, if we're analyzing the symmetry of a structure, we might play with the tolerance a little bit. So here we can see a tolerance number line, and we're calculating the symmetry along this number line. And we can see that for tighter tolerances, we observe lower symmetry, so space group 11. But if we loosen the tolerance, we can get higher symmetry, so we're capturing more symmetry elements. But one thing that we need to keep in mind is that we may have these void regions. And so in this case, maybe we found inconsistent symmetry that violates crystallographic conventions. So instead of throwing an error, we perform essentially an adaptive tolerance scheme or a tolerance scan that changes the tolerance value around this epsilon 0, and we calculate the symmetry at different tolerance values until we find consistent symmetry. So again, this helps us to find results regardless of what tolerance value you choose. And then the last thing I want to mention is that we have, by default, we use system-specific tolerances. So we take into account essentially the resolution of the crystal. So we do a neighbor analysis, and we essentially have preset tolerance values that corresponds to our system. So in this case, epsilon tight, which is based on the minimum interatomic distance divided by a factor. And one thing I want to mention is we use one global tolerance throughout the entire software package, symmetry package. While other packages, you may need to specify angle tolerances or tolerances for lattice vectors. And so that can be quite cumbersome if you're a user to specify and play with these tolerances. So then your next question might be, well, how do you compare to some of the competitor or the other packages in the field? And so we've done this benchmark. So we took a set of experimentally determined structures from the inorganic crystal structure database, and we compared the experimentally reported space group, and we compared it to the space group calculated by one of these packages. And so here we've plotted the mismatch, the number of mismatches. So when experiment and the space group calculator don't agree. And so in this case, you can see AFLOW, which is this blue box here, has the smallest number of mismatches with respect to experiment. So it's the most consistent. Alternatively, if you look at some of the other packages, you can see that there's some variability and they have some higher mismatch counts. And we also gave the symmetry packages essentially another chance. So originally we used their own default tolerance values represented by these solid bars, but we also changed their tolerance value with these hashed bars. And so you can see that we're getting slightly different results, maybe if we change the tolerance. But what this highlights is that if you use AFLOW, you don't need to play with all of these tolerances and it's automatic. While if you use these other packages, you may need to play with the tolerance values to get commensurate results. Okay, so I'll briefly highlight some of the symmetry attributes you can calculate with AFLOW. So here's just a short list. This is by far not exhaustive, but we can determine the symmetry elements for the lattice, so the symmetry of the lattice points, the dual of this, which is the Brillouin zone symmetry, Patterson symmetry, space group, and many different other attributes. We also provide different representations for the symmetry elements. So for example, we've been talking about linear algebra, so we have these 3x3 matrices for rotations, axis angle. If you're familiar with Lie algebra, we also provide the SO3 and SU2 matrices. And compared to other packages, they may only give one or two of these representations. And lastly, we're also consistent with the international tables for crystallography. So this is the standard when it comes to space group symmetry. And so we can calculate the symmetry and essentially map it back to this convention, so we can give you the Wyckoff positions and the space group settings. And so before we go to the Colab notebook, we also have a lot of this functionality online. So you can upload your geometry files to online. So there's an aflow.org online button, and I'll show that a little bit later. But you can actually upload the structure and then calculate it with certain buttons listed here. And we've also seen an entry page on our database. And something new that we've added is that you can visualize the symmetry elements in the JMOL viewer. So hopefully this video plays and you can see that we're performing a C4 rotation. And so you can see how this rock salt structure maps back onto itself. So this is a nice teaching tool, or if you're just having trouble visualizing the structure, this tool has recently been implemented for all of the entry pages on the aflow.org repository. Okay, so now we'll go ahead and do just a few exercises. So again, we should already have this notebook open. So since we've already downloaded AFLOW, so hopefully everyone can see this. And so again, this is the 2 AFLOW structural analysis notebook. And we should be at step 3. Hopefully you saw something like this where it gives you the AFLOW version number. But to verify, you can run this cell, AFLOW ---- version, to test if it was actually successfully installed. If it wasn't, feel free to reach out to the AFLOW team via the chat. Otherwise, feel free to just follow along, and maybe later on we can help you install this and you can run it after the session. Okay, so this next cell, we need to download some structure geometry files that we're going to analyze. So go ahead and run this download data for the notebook. So you should get a zip file and it should give you some structures.
Can you make it a little bit bigger?
Sure.
Yep.
Okay, hopefully that's a little better.
Yep.
Okay, so we're going to start with this AFLOW-SYM section. We don't need these requirements for the notebook because these are already available to us via the Colab. And one thing I want to mention is that typically the AFLOW functionality is available via command line. But we've recently been extending the code, or essentially creating wrappers for Python. And so this is, we're trying to make it easier for people to integrate the AFLOW functionality into their own workflows. So while the different methods exist, I'm just going to focus on Python since we're in a Colab notebook. But let's go ahead and run this cell. So this is the AFLOW Python module. So it wraps around AFLOW, and it allows us to perform the AFLOW commands. So you can look at this at your own time. We're not going to go into the details of this. But so we scroll down, and now that we've loaded this cell, we want to load the class. So in this case, we're going to also import a library, the pretty print. So this is nice for just displaying Python dictionaries or JSON objects. And then we're going to run this line, which instantiates the particular class or the module that we just loaded. So if you run this cell, then you should have all of the AFLOW commands accessible for the symmetry. And if you want, there's the command line functionality hidden. So if you want, you can actually see how we would do this via command line. But again, we'll just leave this as an exercise for later if you're interested. So the first thing we need to do is we want to generate a structure. And I'm actually going to talk about this later, how we actually generate this. So you're kind of just going to have to take my word for it in this case. So, but if you run this cell, what it's doing is we're actually generating the magnesium oxide rock salt structure. And again, I'll go over this a little bit later. And so we've saved this to a file, mgo.postcar. So let's go ahead and do an example. So let's calculate the space group number and standard label. And so in the Python module, we would use the get_sg_data, which stands for get space group data method. So what we need to do is we need to open the file. So you can do with open mgo.postcar. We're going to read the file and we're going to open it as this file handler here. And then we'll input it into this get_sg_data function and we'll run the cell. And since this will return a JSON object, and we're actually going to extract the certain keyword value pair that we're interested in. So in this case, it's the space group number and space group Herman Maguin. And if we do this, I already ran it. So it's space group 225 as expected. And here's the symbol. If you want the Wyckoff positions, again, it's actually the same method, but instead, we're just going to query a different keyword. So again, we're just going to do this for completeness. We're going to rerun this and print out the Wyckoff positions. So this gives us the Wyckoff letter, the multiplicity, what atom is on this particular Wyckoff site, and the position. And then, so you might be wondering, well, what does this sgdata command give us? So if we go to step 3, we can actually just print out the entire JSON object and see what it gives to us. So along with the space group data, sorry, I'm zoomed in a little bit. Oh. There we go. So it actually gives us quite a bit of space group information. So the AFLOW symbol, again, the Wyckoff position. And so this, again, is the keyword and then the values. So the crystal class, if you're familiar with the ITC, this is the general Wyckoff coordinates here. If we scroll down, and we can also see some of the space group information as well. So this is all of the space group information that is given to you. If you'd like other crystallographic descriptions, so if you go to 4, maybe you want things like the Pearson symbol or the lattice type. And so with this, you would use the get_edata method. So again, we do the same prescription. We load the file, and then we use this get_edata function. Oh, didn't mean to create that cell. And so if we run this, and get_edata stands for extended crystal group data. And so we're going to print out the entire JSON, the Pearson symbol, and then the lattice type in particular. So this is the entire JSON objects that returned. You'll see we have the different lattice types, Pearson symbol. Again, we have some of the space group information that we saw in sgdata. So it contains that subset. And I don't want to scroll too fast, and then also we see some of the point group information. So there's actually quite a bit of information here. Due to time, I'm not going to explain each one, but we do have READMEs for this that I'll show at the end that describes these keywords. And then at the very end, I think I asked to print particular keywords, so this Pearson symbol and the crystal lattice type. And then if you want the symmetry operators, so for example, if you want, as I mentioned, there's the different descriptors, the lattice point group, and these are the keywords associated with this analysis. And so if we want to do this analysis, get symmetry, it provides all of the symmetry elements for these different crystallographic symmetry groups. And so if we run this cell, I'm just printing out the number of, or the cardinality of the symmetry groups. So somebody asked, is there a tool for checking distortion modes between structures like isodistort? So in this case, no, we don't have essentially a distortion tool. There is, maybe we'll get into this in the last section, we do talk about crystallographic similarity. So we do compare, and so you can compare, if you distort a cell a little bit, how much the original cell compares to the distorted cell. So you can get a metric for that. But I don't think we have an exact analog to isodistort. No problem. Okay, so these are all of the point group of the cardinality, and here we printed a particular symmetry object. So what actually is returned if you grab a particular instance? So as I mentioned, we give you the rotational matrices, the Lie algebra, and so this is how you grab all of this data. And so again, I've gone through this very quickly, but if you want, we have a README. So if you're in the command line, so use this exclamation point to exit the Python environment, and you can run a command line command call, and this will give you a README on the different symmetry tools that are available. So again, I've just done a high-level overview, but feel free to look at this later on. And if you're interested, we also have the article shown here. And so again, if you want an overview of crystallographic symmetry, we also have some details in this article. Okay, so I know I went very fast, but are there any questions about the symmetry tool at this point? Feel free to post in the chat. I guess while I'm waiting, if there's any questions, there are these extra functions and options. So if you want to play with the different space group settings and tolerance, I've added some cells that you can execute, but this is just for your own, if you'd like to play with it on your own. So yeah, let me go ahead and do a polling. Okay, so let's just see where everyone's at. Does this make sense? Okay, so I'm seeing yes and yes mostly. Mostly is yes mostly, and that's understandable. I apologize. I'm trying to cover a lot of ground, and but yeah, again, if you have any questions, oh, we do have a question. So does a monoclinic system in Cartesian space yield a cubic system in fractional space? Okay, so I think I get where you're going. So technically, the symmetry, it's always a monoclinic. If you have a monoclinic system in Cartesian coordinates, the way you're representing the crystal, that's what's changing. So when you convert to fractional space, you're essentially changing a representation. It doesn't mean that we've changed the symmetry, we're just changing a representation. So even if you convert the system to a fractional space, it still has monoclinic symmetry, but we're forcing it into this cubic representation, if that makes sense. So hopefully that makes sense. Okay, excellent. Okay, so I'll go ahead and close the poll. Again, if you have questions about symmetry, feel free to ask later on, and I'd be happy to discuss it further. Okay, so next we're gonna go back to the PowerPoint, and now we're gonna be talking about prototypes. So we're actually gonna be generating crystal structures with the AFLOW software. And Cormac and Marco have already alluded to this, that we have built-in structural prototypes. So for example, the Heusler structure, which serves as a backbone structure that we can decorate with different atomic species and create hypothetical new materials that we can run simulations on. And currently we have 600 prototypes available online, and I'll show that in a little bit. And so we've been working on this effort for quite a while now. So it's the AFLOW Prototype Encyclopedia, which has been a synergistic effort with Professor Mike Mell. When he was at the Naval Research Laboratory, he started this endeavor. And so we provide many different descriptors for the different prototypes. So labels, Wyckoff positions, symmetry descriptors. And then the idea here is that we wanted to integrate this with the AFLOW software, so that way we could generate these structural prototypes automatically by decorating them with different elements. And so originally, Mike started with part 1, which had 288 prototypes. And since then, we've extended it to part 2, and we currently have 590 available online. And there's at least one representative from each space group. And part 3, we're actually working on it right now. We have another, I think, 510 structures ready to go. And so that'll probably be online shortly. And so I just want to briefly mention this idea of a standard designation. So when we create these structures, we want to have a way to, an intuitive way to generate the structure programmatically while also giving us information on what the structure looks like. And so we do this with the AFLOW label and parameters. And so this AFLOW label is a string separated by underscores, and this tells us essentially what the structure looks like. So in this first field, it's the stoichiometry, second field, Pearson symbol, third space group, and the subsequent fields are the Wyckoff letters associated with each site. So in this case, site A has Wyckoff letter B, and so on and so forth. And so this alone isn't enough to generate a structure because there are degrees of freedom that we need to specify, such as the lattice parameters or certain coordinates. And so we need the AFLOW parameters. But here we only need a finite subset. So we only need the lattice parameter A, C over A, and then these are actually Wyckoff Z coordinates. And so why this particular subset? So these particular variables are consistent with the symmetry of the structure. So if we were to tune these parameters, we would generate, for instance, a new structure that's maybe shortened, or maybe the atom positions are changed. But even by changing this, we're preserving the symmetry. So we're not breaking any symmetry here. So even though this is one command with a certain set of parameters, you can actually generate many, many structures with a single label just by changing the parameters. And so this is our method of generating these structures. And so it's very powerful because, again, it's not just one structure, but you can generate many. So let's go ahead and see this online. So you can feel free to follow along. So if you want to go to a web browser, and we'll go to AFLOW.org. And this will take us to the main AFLOW webpage. And if we scroll down, as Cormac mentioned, we have some applications. And so we're interested in the Crystal Prototype webpage. And so again, I'm going to zoom in a little bit just so we can see. Hopefully that's okay. And just in case anyone's having problems accessing the site, let me give it to everyone. This is the alternative link. So if it's running slow, feel free to use the link that I posted in the chat. So on here, we can see that we have the library of crystallographic prototypes. We have 590 currently online. And you can search the prototypes by different attributes, such as the space group and Pearson symbol. And then we also, again, there's these tabs at the top. And then if you're interested, maybe you're not familiar with crystallography or maybe the lattice types. So we have some useful introductions to the different lattice types and the space groups. And so we also have search functionality. So let's go ahead and click on this search button in the middle of the page. And it should take you to this page. And so you can search, this is just a bare bones search tool. So you can search the prototype by name, space group, Pearson symbol, or structubric designation. So let's go ahead and search for corundum, hit enter, and this structure should show up. So if we do this, this will take us to a particular prototype entry page. And so all of them have the same structure, so I'll just go through this one. But on each page, we have a JMOL viewer, so you can rotate the structure and change the way that you're viewing the structure. Below this, we have the general prototype information, so symmetry information, and the prototypical element or compound that exhibits this structure. We also provide some information. Maybe there are other compounds that exhibit this structure, maybe some useful comments when we are going through the literature. And then we provide the primitive vectors and the basis vectors. So these are the lattice vectors and atomic coordinates, essentially. And you'll notice that they're given in symbolic notation. So again, they're given with respect to A, B, C, alpha, beta, gamma, and X, Y, Z. And so again, this highlights that you can change these parameters and keep the symmetry and generate a similar structure. And so we also have the references, so where we found the structure, some files that you can download. But at the bottom, probably the most important part is the prototype generator. So again, I've mentioned this idea of generating the prototypes, and you can change these degrees of freedom, and then you can create geometry files. So for example, if you want the VASP output, or quantum espresso, and you can see that in the output, we're generating these files. And so this is nice because it actually interfaces with the AFLOW software online, and you can generate many different structures. And so these are the output formats that AFLOW can understand. So you can pass these in as an argument, or it can actually print these out in these different formats. So that's the online tool. I guess I'll do a quick poll to see if that makes sense or if anyone has any questions about the online tool. Polling. Okay. Can we also input defects in doping? So the answer is yes. So we do actually have a disorder, a way to model disordered structures. So again, you can insert, you can model disordered structures but we're not going to get a chance to go into the details of this. And so you might have defects and we can model these disordered structures. But again, if you'd like to learn more, there's the AFLOW School page that we have on our website. Or if you're interested, we can also talk about it more in the future. But yes, good question. Okay, so it looks like more or less everyone's following. Yes, and Corey posted the link to the AFLOW School, and we talk about disordered structures, modeling disordered structures a bit more there. Okay, so now let's go ahead and navigate to the Colab notebook. So again, it's the same one that we had open, the Symmetry one. But now we're at the section 2 for the prototypes. So before we were working with Python, but I think it actually makes more sense to use the command line syntax since we're actually creating geometry files. And so we're going to use the command line version, but there is a Python module if you'd like to integrate it into your workflow. So this is the general syntax, and this is here for your reference, but we're actually going to walk through this step by step to see how we generate a structure. Okay, so let's go to this first example. So we're going to generate the magnesium oxide rock salt structure. And so to do this, again, we're using the command line. So we are leaving the Python environment with this exclamation point. And the command is as follows. So it's AFLOW -- proto equals, so this says we're going to generate a prototype that has this label. So this is the label for the rock salt structure. Again, you can see that it has space group 225. And then we want to decorate it with particular elements. So in this case, magnesium and oxygen. And so to do this, we append the species with colons. So :MG, :O. And in general, the convention for AFLOW is to always put this in alphabetical order. And this is really important when we generate the AFLOW-in file, which we're not going to really discuss today. But the convention in AFLOW is always alphabetical order. And so if you actually want to swap the species, so decorate them on different sites, I'll show you how to do that in a little bit. So this is the general prototype command. And then in this case, there's 1 degree of freedom that we have to specify. So we do -- params equals 3.5. So this is the parameter for the ALAS parameter. So if we run this, by default, it generates the rock salt structure, or it generates the rock salt structure in a postcard format, so VASP. And so if you're familiar with this geometry file, so we have the scaling factor, the lattice vectors, the number of each type of element, and then the coordinates. And again, this is in direct coordinates, as I mentioned, or fractional. So again, you can see they're all between 0 and 1. And so if you want to generate different file formats, so as I mentioned, AFLOW supports a few common formats, so CIF, AIMS, Quantum Espresso. And so you can use the same command, so this AFLOW -- proto, and then same command, but you append this flag. So in this case, if we want the CIF file, we do --CIF. And so if we run this, it's going to generate a CIF file for this particular structure. And so this should look familiar if you're familiar with CIFs. If you want Quantum Espresso, you can change this to QE and run the cell again. And it's the Quantum Espresso file format. And so I mentioned maybe you want to change or swap the decoration. So maybe on the first site, you want to do the second element instead of the first element here. So in this case, we use the site decoration designation. So again, it's the same command, but right after the label, you put a dot. And then in the case of a binary, the two choices that you can decorate are an AB decoration or a BA decoration. And so by default, it does the alphabetic order, so AB. So, but in this case, maybe we want to swap the sites with BA. And so in this case, if you remember to the previous postcard, magnesium was on the origin. But in this case, now we've swapped it. But you can see we've preserved alphabetic ordering of the species. And so this logic extends to ternaries, quaternaries. So again, if you want to do a ternary, you can do ABC, and then there's 6 different possible permutations of the decorations. So you can play with this using this, this feature. Another feature I want to mention is this automatic volume scaling. So for example, we want to do things at a high throughput level, and maybe we want to decorate the structure with different elements. So again, these are backbone structures, and let's say we add in maybe larger elements that have a larger atomic radii. The volume might change. And so we want an initial guess for this, and so we use a Vegard's type scaling law to estimate the volume of the crystal based on what elements you're decorating with. So to do this, it's the same prototype command and the parameters, but instead of specifying a positive lattice constant, we put a -1. And this signals to AFLOW, okay, read what elements are in here and do the Vegard scaling. So let's see what happens. So again, you'll notice the structure looks the same, but actually the scaling factor has changed. It's now negative. And a negative value in the VASP geometry file signals a volume. So let's actually change the elements and see how this is affected. So let's do chlorine and sodium. So sodium chloride. So right now it's -30-ish. And if we run this now, it's -58. So again, this is an initial guess for this particular compound using this Vegard scaling. And so the last few things I want to mention about the prototypes are, right now we've kind of been using an easy example, rock salt. You only need to specify one parameter. But as you get to lower symmetry, you might need to specify actually many parameters. So for this chalcostibite structure, you have to specify many degrees of freedom. And so you can do this just fine with the normal prescription, but maybe you don't want to type this out every time. And so we've actually enumerated the parameter set. So in this case, if you just append to the label minus and then 001 is the designation, and then the similar prototype command, but now you don't need the parameters. And so if you do this, you can see actually we've generated the same structure. So if you look in the title line, it tells you what parameters were used. And with this enumeration, you can see that it used the same parameters, but we've just essentially aliased the parameters. So this is, again, an easy way to do this. And you might be wondering, well, how many aliases are available, or how many parameter sets? So if you just run the prototype command with the label, no parameters, you'll get an error, but the error will actually give you information, and it says that this particular label has 3 preset parameter sets. And these are the aliases, and then these are the values. And so this is, again, if you're not sure what parameters you need to specify, this is a nice feature. Okay, so again, I've gone pretty fast, but there are many different prototypes that are available. And if you want a full list, you can use the AFLOW -- protos command. So protos with an S. And if you do this, it'll give you the full list of prototypes that are available in AFLOW. And so you can see the typical designations. And at the top, I didn't really get a chance to talk about it, but there are also there are some more prototype labels that don't require parameters. And so again, if you want more information on this, we have a README at the bottom here. And so you can see more information there. And I'm actually going to skip this next part. This is if you want to filter the prototypes, there are some commands to do that, But again, for the README, we're just gonna, I'll leave that for you to look at the README and do that on your own. Okay, so again, I'll do a quick poll. Hopefully that makes sense to everyone. Again, feel free to ask later on. But it seems like for the most part, people are, yes, mostly following. So it looks like I have a few more minutes, so I'm gonna go, I think, fairly quickly through this next section. And this is the AFLOW-XtalFinder. Okay, so in this case, this last tool, I've been talking about crystal structures, and let's say we have a large data set that we're working with. And so maybe we want to make sure that there are no duplicate structures in the data set that we have. And so this is particularly important for data mining and statistics, and also for machine learning, since we don't want to bias our machine learning training models because we have duplicate structural entries. And so we want to have an automatic method for removing duplicates or identifying them. In addition, maybe we want to find common structure types. So given different compounds or decorations, we want to find an underlying backbone or prototype structure. And we may also want to classify it. So be able to label this as, this is the rock salt structure. And so this is the motivation behind this tool, but we have a caveat that we need to consider. And so in this case, we're modeling a macroscopic crystal. And so when you're doing this, you're creating a finite unit cell, so it has a finite number of elements, and you can represent this with different unit cells or origin choices. So in this case, this is all the same crystal, but they're in different representations. So we need a programmatic way to determine the similarity regardless of what representation the structure's in. And so this is the motivation behind this tool. And so one thing the tool can do is it can classify. So if you're given an input structure, it can actually cast your structure into the prototype designation that I've shown. And this is important because, one, it's consistent with the international tables for crystallography, the standard. It's tunable, so you can change these parameters and modify the structure. And then it's also regeneratable with the software. And so this is a nice feature to cast it into this representation, which again could also be used as a feature since it has symmetry information. Sorry, I jumped forward a little bit. So what are the different, okay, there we go. So what are the different levels of comparison that we can perform? We can perform symmetry comparisons, excuse me. So we can take two structures regardless of the representation, and we can calculate the symmetries, determine things like the space group and Wyckoff positions, and then we can compare the symmetries to see if they're similar. And so what this does is it determines isopointal structures, meaning that they have the same symmetry. So this is essentially the first tier of comparison. So they have similar symmetry. We can go a step further and look at the local atomic geometry. So this is kind of giving us, if we zoom into the crystal structure, we're getting snapshots of what the structure looks like centered around an atom. So this is the local atomic geometry. We can compare angles, coordination, and this will give us a snapshot comparison, if you will. So this is the second tier of comparison. And finally, we do a robust geometric comparison. And so in this case, we're trying to map two crystal structures onto one another and determine the level of similarity or dissimilarity. And so in this case, we take two structures, perform a supercell expansion on one, and try to find a similar representation to this input here. And then we need to quantify the difference between the two representations. And so we borrowed inspiration from Bertzlov and Malinowski with this misfit quantity as a metric to quantify similarity. And so this is based on how the lattice faces differ, how the coordinate displacement, so the atom positions, differ, and then there's a penalty if you can't map the atoms. Maybe they're too far apart or maybe even missing. And so there are ranges of this that have been defined by these authors, and we've actually validated this in the work that we've done. And so these are nice ranges. So if the misfit is less than 0.1, the structures are the same. And if they're greater than 0.2, they're not a match. And so this will tell us whether or not two structures are isoconfigurational or exactly the same. There are different comparison types. So if you want to compare structures based on whether or not they're decorated with the same compounds, that's a material type comparison. There's the structure type, so to identify backbone structures, so it ignores the elements and compares the structure. Decoration type, so given this particular structure, what are the different ways that you can decorate them and still have them be distinct decorations? So that's this comparison type. And then also you can introduce the magnetic moment. So here you have two antiferromagnetic structures, and maybe you want to know whether or not they are the same. And so you can actually perform this mapping with the AFLOW-XtalFinder tool. And this will give you distinct spin configurations. And so I'll highlight this briefly. We can perform many comparisons at once via the scheme. And so you don't need to do just one at a time. AFLOW will automatically aggregate the structures into equivalent sets. And there are two last things that I want to mention is that you can compare your input structure to the encyclopedia. So maybe you want to find if your structure maps to anything in the prototype database. So in this case, AFLOW will do this for you. You input the structure and return that, okay, this is the Half-Heusler structure and the information associated with it. And then you can also perform a database comparison. So given an input structure, you might be asking, does this exist in the aflow.org repository? And so this actually uses the AFLOW functionality that Marco mentioned. And so you can perform, the XtalFinder is performing the AFLOW query under the hood. It's grabbing all of the relevant structures, comparing them, and then listing the equivalent structures in the database. And again, with the AFLOW functionality, you can query the enthalpy per atom, for instance, and you can see that we've actually printed this, and you can see that all of the similar structures have similar properties. So this is highlighting the structure property relationship. Okay, so it looks like I have maybe a few more minutes. So I'm just gonna go ahead and go to the Colab notebook. Again, it's the same one that we've been working with. And I'm just gonna go briefly maybe through one or two of the cells so that way we can get on to Corey's session. Okay, so we need to, again, we're loading this Python module, back to Python. And there's quite a bit of information here. You can look at this later on. And then you load the class. And then if you want to convert a structure to this label designation, you use the get prototype label method and you input the structure here, so the corundum structure, and it provides the AFLOW parameter, the label, parameter list, and parameter values. So we've casted it into this structure. If you want to compare materials, so like I said, maybe you have multiple material compounds you want to compare. So this is a directory of structures. And let's go ahead and compare them. So this cell might take a few seconds to run. So let's run it. But what we're doing is we're taking this directory, structures, and then we're using this compare materials directory method. And we're inputting the directory, and then we're printing the number of unique materials, so just the length of the object that's returned. And then here, this is just grouping the structures into equivalent sets. So there are 9 unique materials here, and you can see that they're grouped into sets. So this is the representative structure, and then the duplicates. And it also prints the misfit value here. You can do the same for this compare structures. I'm not going to run the cell, but it does the same idea. But in this case, you do compare structures, and it ignores the elements. And so this will find the backbone prototype structures that are similar for this set of compounds. Again, you can compare to the AFLOW Prototype Encyclopedia. So we have this mystery postcard. If we run the cell and you use the compare to prototypes method, then when you run this, this will return the AFLOW prototype labels, how closely they match to your input structure with this misfit value. And then the last thing, is compared to the database. So let's go ahead and create a rock salt structure, save it to this file, and then we're going to run this cell. It's going to take a few seconds. And you use the compare to database method. And in this case, we're querying certain API keywords, the enthalpy per atom, the number of atoms, and for fun, how long the calculation took. And then we're going to print all of this information out to the screen. Takes a few seconds. Hopefully it finishes. I think it runs a little slower in Colab, but again, we're querying the entire database and comparing the relevant structures. So it looks like it's still running, so I'll briefly highlight that we have the README as always, and then an article. Oh, here it is. So these are the results, the AURL, the misfit, and then the properties we queried.